For over 50 years, human exploration has been confined to low Earth orbit. Reaching the Moon, and eventually Mars, requires overcoming a massive gravitational hurdle that demands more thrust than any rocket in history. NASA's Space Launch System, or SLS, was engineered as the physical architecture to break that barrier. It is designed specifically to carry the massive payloads and human crews necessary for deep space transit. The climb to space begins at T-7 seconds. The four RS-25 liquid propellant engines ignite, burning supercooled hydrogen and oxygen, while flight computers verify they have reached full power. At T0, the twin solid rocket boosters ignite. This provides the majority of the thrust for the first 2 minutes of flight, a violent acceleration that pushes the vehicle through the period of greatest atmospheric force. As this chart indicates, the Block 1 configuration generates 8.8 million pounds of thrust, delivering 27 metric tons beyond the Moon. The architecture scales up to the Block 2 configuration, increasing thrust to 9.4 million pounds and raising payload capacity to 46 metric tons. This scalable design ensures the SLS is not a single-use vehicle, but a long-term transportation system. It provides the heavy lift capacity needed to launch the infrastructure for a permanent presence in deep space. This hardware faces its first operational stress when the Artemis II crew reaches the lunar far side. At this distance, the astronauts are further from home than any humans in history. Out the windows of the Orion spacecraft, the crew observes a rugged, heavily cratered terrain. They see specific geological features like the Vavilov crater and ancient lava flows that reveal the Moon's volcanic history. Navigating this environment requires managing intense technical constraints. As the Moon blocks the spacecraft's line of sight to Earth, the crew enters a planned 40-minute communications blackout with mission control. The crew operates in a high-pressure sensory environment. They must use eclipse viewers to observe a solar eclipse, while simultaneously operating handheld cameras to capture high-resolution imagery under rapidly changing light. Managing these systems in total isolation demonstrates that human crews can maintain flight operations without a constant link to Earth. These 40 minutes of silence are a prerequisite for the much longer periods of autonomy required for a voyage to Mars. As the spacecraft's trajectory brings it back toward the near side, the geometry of the orbit creates a rare visual event. The Earth appears as a delicate crescent, slowly slipping behind the pockmarked lunar horizon. This is the Earthset. The bright, cloud-streaked blue of our homeworld stands in sharp relief against the dead, gray crust of the lunar foreground. The image connects this mission to the legacy of Apollo 8. While that crew captured the famous Earthrise in 1968, the modern Artemis astronauts are now looking back at their home from the same vantage point. This photograph shows Earth as a tiny sliver of light, small enough to be hidden by a single lunar crater. Seeing our entire world reduced to a fragile, distant outpost against a desolate horizon reframes the planet not as the center of the universe, but as a small starting point in a much larger cosmic ocean. The engineering and psychological milestones of Artemis serve a broader strategic objective. Every phase of these missions is designed to solve a specific problem facing the eventual transit to Mars. The Moon acts as a training ground, where every lunar flyby and landing is a calculated rehearsal. NASA is using these missions to refine the life support systems and operational procedures needed for deep space survival. Part of that rehearsal involves the Avatar experiment. By measuring how radiation exposure increases as a spacecraft moves away from Earth's magnetic protection, researchers can develop the shielding required for a multi-year trip to the Red Planet. The upcoming Gateway station in lunar orbit will expand this research. It provides a long-term staging point that mimics the orbital operations and deep space habitation necessary for sustainable Martian exploration. The SLS Block 2 cargo configuration provides the specific volume needed for these missions. Its capacity for nearly 35,000 cubic feet of payload allows NASA to launch the massive habitats and fuel supplies required to keep humans alive on Mars. The Earthset captured by Artemis II is a visual promise. It shows that we have built the physical architecture to reach the Moon, and more importantly, the resilience to leave it behind for the ultimate journey to Mars.